All right, time to start. Good morning, good afternoon, and good evening. Welcome to the third day of ASRX 2020. I'm Li Qin Chen. It is my great honor to introduce Dr. Vadim Lyubashevsky. Vadim is one of the most distinguished researchers in lattice-based cryptography. He received his PhD in 2008 from the University of California, San Diego. The title of his thesis is Towards Practical Lattice-based Cryptography. Since then, he has carried on working in this research area. After his PhD, he spent 2 years at Tel Aviv University as a postdoctor. In 2010, he became a researcher at INRIA and ENS in Paris. Since 2015, he has been a research scientist at IBM Research Zurich. Vadim's work on the ring SIS, ring LWE problems, ring LWE encryption, and digital signatures forms many of the most efficient constructions in the ongoing NIST standardization effort. Now, let me hand over to Vadim.
Thanks for that introduction, Lee, and thank you to you and all the other organizers for inviting me to give this talk. I'm very happy to talk about this topic. Yeah, so the topic of the talk is lattices and zero knowledge. So I think that everyone is familiar with maybe lattices, at least heard of them, and certainly zero knowledge. But so I want to kind of give a talk to say, these two actually go very well together, could go very well together in the future. So the goal of this talk is to kind of introduce people to lattice-based zero knowledge. So and it's I want to show a glimpse of the similarities and differences between how you construct zero knowledge proofs for lattices versus a somewhat similar high-level topic. How do you do it for discrete log proofs? So then I also want to describe some situations why you would want to use lattice-based zero knowledge. So I think even though the field is really just beginning, I think it's already one of the better quantum safe options for some expressions. And I hope this encourages people to at least, to sort of look at it and start working on it and improving the fundamentals, because really now this is the ground level of it. The research has just started. I think we are with lattice-based zero knowledge where we were with just regular lattice cryptography maybe 10 years ago. So 10 years ago it was mostly a theoretical topic, but now it's really sort of a mainstream topic that even gets talked at security conferences, not just cryptography conferences, but at more applied ones. So let me just just a 1-2 slide brief overview of what is zero knowledge. So just the typical use scenario is that there's some function f and some output f of x equals y, and the prover, he knows fx and y, but the verifier doesn't know x, he just knows y. And the goal of the prover is to present a transcript, so he gives some sort of a proof or a transcript to the verifier, and it should do 3 things. First, well, if the prover is honest, the verifier should accept him, say yes, whatever you're saying is true. 2 is, well, it should imply, what the prover is saying is that he knows x. So looking at this transcript, the verifier should be convinced that the prover does indeed know x. And the third property, that's the zero knowledge property, is that this does not reveal any additional information about x, except the fact that the prover knows. Now, there's been a lot of recent work in the current year, in the the few last years, even ongoing now, and a lot of it is inspired by applications to blockchain. Um, and so if this distributed computing, this blockchain stuff really does take off, and this is very separate from cryptocurrencies. I would say cryptocurrencies, Bitcoin maybe is not so important, but maybe the blockchain applications really are, and zero knowledge does form a foundation for basically using blockchain, using these distributed ledgers. But it also has other applications. Even before blockchain it had applications, but the money's in blockchain, so a lot of research kind of has happened there, and it really advanced the state of the art of zero knowledge. And the recent constructions of zero knowledge proofs have some actually additional nice properties. So not only does it prove knowledge of X, but the proof is actually can be actually a lot shorter than X, and also the verification time can also be a lot shorter than X. All these proofs have fancy names like bulletproof, sonic, supersonic, Marlin, etc., etc. Planck, and so the nice thing is, these proofs are very, very practical, and they have outputs of just a few kilobytes for proving very large instances. So this proof transcript being shorter than X is really, really shorter than X. It's basically logarithmic in X. And so it really is just a few kilobytes, and this is very useful. But so, the one kind of downside, I mean, not yet, but maybe in the future, is that all of these are based on classical hardness assumptions. So, discrete log, factoring, and, pairing stuff, variations of these assumptions, some stronger assumptions, but all classical ones. So kind of the thesis is that if quantum computing comes soon, you really cannot use these proofs anymore. So quantum computing, right? That's been a very hot topic. It's been on the lips of many people, but the question is, when is it coming, right? That's something that everyone always asks. Yes, we've heard about it. It's going to be devastating to cryptography. Is it coming? And if so, when? So I don't know, right? So I think we're sort of sure of three things, what will happen. At least people who believe that quantum computing really is possible. There's still a minority of people who don't believe it's possible. But I think, the majority do think that eventually we will have these quantum computers that do something. So we think there's a few stages of it, right? First, we have to make quantum computers good for something. And this is usually referred to as quantum supremacy. So make a quantum computer so that it can solve some problem better than any classical computer ever can. Okay, so once we achieve that, then we want to make quantum computers good for more than just one thing. And then you have to really start working on the engineering, reducing errors, increasing qubits, et cetera, et cetera. And if you do this well enough, eventually you will be able to use Shor's algorithm, and you'll break 256-bit ECC crypto. So that will really be, that's going to be a milestone that, yes, you can really break, today's crypto really is broken. And then, that's not over then, because I don't think the goal of, the industrial goal of quantum computers is not to break cryptography. It's really to accelerate all this quantum chemistry and financial stochastic process analysis. So do things like that with a quantum computer. And then, so they'll, of course, keep improving it. And, maybe there'll be some sort of a new Moore's law, right, for quantum computers. And, who knows what's going to happen. So then, of course, when you give this, this sort of graphic, people want to know, when, what are the dates? When is it going to happen? And unfortunately, here, this is one of these things where you really don't know, right? So, it's really hard to say what's going to happen. In some way, we can't even agree where we are now, right? So some people say, well, we didn't really have, we are still working towards making quantum computers good for something. Others say, no, our quantum computers really are already good for something. So now we're just working, now we're just kind of in the second stage. So, we can't even agree where we are now, right? And that's partly because this quantum supremacy, make quantum computers good for something, is not really well defined. I really like this quote by a scientist from Alibaba in 2018, he kind of said that for device physicists to worry about when to reach supremacy is like worrying about when your baby is going to be smarter than your dog. So, just focus on taking good care of her and it'll happen, even though you aren't sure when. So this is pretty good. Because you never really know when your baby's going to be smarter than your dog. And maybe I would even add to this quote that's saying it's actually harder than that. It's not just your dog; it's every dog, right? So maybe you taught your baby to count to 10, but then somebody pulls out some dog from somewhere who's been practicing counting to 10, and that's all it can do. Can't fetch or anything. And there, all of a sudden, you thought your baby was smarter, it was achieved supremacy, and turns out it did not, right? So in some sense, it is kind of a very moving target as well, this quantum supremacy. You're not really sure. You really want to get to somewhere where you really are sure. Yes, quantum. We definitely are. We definitely have achieved it. It's really in our rear view mirror. So, but the exact point is not really where we want to. So let's just say we're kind of around there. Okay. So now still, this still doesn't tell us when will we get to, break this 256-bit ECC crypto. So Google made a prediction, a couple of months ago in the beginning of the year, that, they will reach 1 million qubit in 2030. Okay, so that's actually somewhat of a, if that is true, that's somewhat of a good reference, because you need maybe, 10 to 20 million qubits to break to run Schnorr's, to break ECC crypto. So now that would really be worrisome, right? Because now you're really within an order of magnitude of where you need to be. So that would be quite scary, and really then I don't think there'd be very few skeptics who say, oh no, you can't break. No, then really it's going to be broken, just a matter of time. And of course, then the people still ask, okay, but fine, that's ECC crypto, but what about AES? Should we switch from AES 128 to 256? So that breaking AES 128, so that's a different algorithm, Grover's algorithm, and I think people believe it'll be much harder to run Grover's algorithm than Schnorr's. And at this point, I have no idea, right? This is so far in the future. AES is going to be somewhere here. When people ask when, I say I don't care. At some point, we're going to have, my guess that of alien technology making this all irrelevant is as good as anyone's guess when AES is going to have. So I don't know, kind of, I don't really, the exact dates, I have no idea. But people are guessing that Schnorr's maybe 15 years from now, something should definitely happen. Okay, so then the question is, okay, so you don't know, so I don't know when it's going to happen. It's definitely not going to happen before 2030, almost certainly, given by this prediction. So why do something now? And the main reason is, well, there's the store now, decrypt later attack, right? Basically, anyone can store your communication now and then wait until they get a quantum computer. So this is pretty devastating. So that's the main reason for really acting now. Another reason is that, well, it takes time to properly switch crypto. So even if we know that in 5 years, you need to be ready 5 years from now, it takes time to find what you have to do to change it. So it's a people problem here. And also, for example, in a distributed scenario, so blockchain, or even just a scenario where it's the people themselves that have to do something. So not the system administrators, but the people themselves have to do something. Well, you need to, migrate individually, and that could really take time to get them all right, because people, even the people who, the previous point was it takes time for sysadmins to migrate crypto, but this is actually just ordinary people who will have to, either change their keys or take in their car for a special update. And this is really, you cannot, say 1 or 2 years. If somebody forgets to migrate, they can really be hacked, and this could really cause a problem. So another reason is that, well, while I think that signatures and encryption schemes are kind of done, more advanced things are not, right? So you really, for example, zero knowledge proofs, what I'll be talking about today, is you really are not done yet, right? You may still need to optimally design the crypto protocols. So maybe, you know, we actually need the time to do it. So maybe by the time we actually get them perfect, we really need to migrate quickly. So I think the research has to start well in advance. So now is probably a good time. If this timeline is about 15 years, then this is a good time to start. Okay, but this is not to say that there aren't any quantum safe zero knowledge proofs. There actually are, and they are kind of used. There's this PCP approach of Killian from the 80s and Micali that relies just on collision-resistant hash functions, so it's quantum safe. And there's actually been a lot of recent research, especially IOP, so Ligero, Aurora, that really took this research, which was thought to be theoretical just maybe 10 years ago, and really made it practical. But they do have a few downsides that, you know, even though these proofs are quite short and definitely doable, there is some startup cost. So, you know, they kind of started at a few hundred kilobytes. So, you know, if you want to just prove a short statement, you know, which is just could, you know, take a few kilobytes for a classical proof, this could be kind of long, and it's also kind of big, and it's also not fast. So, you know, even just the basic, just, you know, proving knowledge of a pre-image of a collision of a hash function takes a few hundred milliseconds, and, you know, generally the proofs are much longer, require much more than that. So they're not fast, and there is some startup cost. So maybe we can try to improve on that, for at least start. You know, at least good place to start is to see what's missing in the current literature and try to improve on that, and then maybe eventually even try to kind of, you know, expand on this and even get something that's sort of better, where these Ligero and Aurora already are pretty good. Okay, so now lattices. So lattices really went from kind of a theoretical topic to a very, very practical one in the last decade. So this is it was particularly kind of aided by this quantum safe standards progress. And then, so I'll give you a brief timeline of what was happening. And this is a very USA-centric one. So, I mean, of course, there's been other standardization standards going on around the world, but sort of I'll just focus on the US one for now. So it was kind of jump started. So people have been working on quantum safe crypto for a long time, 2 decades maybe. At least it was kind of brought up as this is a viable thing to work on. But maybe in 2015, the NSA made a statement that the IAD will initiate and transition to quantum-resistant algorithms in the not too distant future. And so they're saying for all the partners, so basically government agencies, who have not yet made the transition to elliptic curve crypto should not do it, and instead prepare for the upcoming quantum-resistant algorithm transition. So at some point, the NSA really, so all of a sudden, they really said, okay, it's, you know, we have to do this. And so 2 years later, NIST, the American standardization body, starts the post-quantum standardization process for encryption and chem, and it receives about 69 proper entries for encryption and signature schemes. So now we are about 3 years afterwards, and it's in round 3, so 2 rounds have gone by, and there's 7 finalists, so 4 for encryption and 3 for digital signatures, and out of those 7, you know, 5 are based on lattices. So the reason lattices are so popular is that they are quite compact. So public key plus ciphertext combined is around 2 kilobytes. For chems, and they're actually faster than elliptic curve RSA-based schemes. For signatures, they're also quite good. So there's you know, public key and signature size is somewhere between 2 and 5 kilobytes. Verification is fairly fast. Signing is a little bit slower, but still, you know, quite fast. You can do more than 3,000 signatures per second. So this makes lattices a very, very, you know, nice sort of you know, basis upon which to base cryptography in the future. So this is what's going on with NIST, and then NSA kind of at the same time makes the statement that, well, they've reviewed the security analysis and they are confident in the lattice-based schemes with strong dependence and well-studied mathematical problems, and in hash-based signatures for certain niche solutions. So lattices and hash-based schemes seems like what, you know, the Americans would like. And so NSA sort of goes on, based on their history, analysis, and implementation efforts, NSA expects that a NIST candidate lattice-based signature and a NIST candidate lattice-based encapsulation mechanism will be improved for NSS. So basically, the NSA is kind of really approving lattices, and of course, this this raised a few issues, like, oh, why are they doing it? Is it because they know how to break it? But I mean, that would be quite ridiculous, because the U.S. government agencies would rely on these things, so you cannot plant the trap door a back door into these things. So really, if you know how to break it, you really are relying that no one else does. And that would be extremely irresponsible. So what I think is that, so I know just from some personal experience, that when I visited NIST in 2014, I think they have these joint seminars, scientific seminars, with sometimes the NSA attends them, and as guys from the NSA attend them. And so when I gave a talk, I mean, the NSA guys they were really, really knowledgeable about lattice cryptography. So it's definitely, when they said we're going to switch in 2015 to something, I don't think they asked the question without kind of already, being a little prepared for the answer. So I think the reason that they're supporting it is they really have studied this for at least a decade, and maybe they have some better algorithms than we do in academia, but perhaps they're sort of convinced, at least they believe, that lattice crypto is in fact secure. So I mean, that's just my my guess. And so NIST in 2022 is supposed to standardize something, and maybe 2024 will actually have the full draft of the standards. So basically, if sort of everything goes as as according to plan, in 2022-24 we will have lattice-based cryptography, which will be implemented. Which will be standardized, and if quantum, there really is this progress towards building a quantum computer, people will see how we actually are moving closer to this million bits qubits thing. Then I think everybody will switch, at least in hybrid mode in the beginning, to lattice cryptography. So if quantum computer research stalls, maybe people will stall from switching as well. But I mean, the standards will be there. Okay, so once you have the basic stuff, you would also need some zero knowledge, some more advanced things. And because right now we are using zero knowledge proofs because our basic signatures encryptions commitments are based on these discrete log problems, factoring, etc. So we need zero knowledge proofs that sort of are also based on the same assumptions. But once our encryption signatures, etc., commitments will be based on lattices, we will need zero knowledge proofs to prove lattice lattice statements. Okay, so now let me just give you a very brief introduction to lattice-based zero knowledge. And something you should think about as you're seeing it is it's like Schnorr, which based on discrete log Schnorr scheme, but different. So from a high level, we are trying to do something that what Schnorr is doing, or what Schnorr proofs are doing, but there will be problems along the way. So let me just give an example and just explain what's going on. So on the one hand, you want to prove a discrete log relation, and on the other, there's a lattice ring LWE or ring cis relation. So I'll sort of explain what ring LWE or ring cis is later. Sort of not important for now. So in discrete log, the ring you're working with over is some ring ZQ. So has addition, multiplication, and ZQ star. For lattices, it's also a ring, but it's a ring, instead of modulo q, it's modulo x to the n plus 1. So it's a polynomial ring, modulo x to the n plus 1. So this is where the secrets live. In the discrete log world, they live in ZQ. In the lattice world, they live in ZX mod x to the n plus 1. But sort of algebraically, they're both rings. Okay, so in discrete log, there's a function that's mapping secrets from this ring in the exponent, right? So you have some generators, G1 through GK, and you raise them to the SI. So normally discrete log, you just defined as 1, there's only one S, but I want to just define it with K of them. But I mean, it's okay, right? So it's the same thing. So there's a function mapping from some ring R to from the ring R to the K to some other ring, R prime. Right, because before it was mod Q and now it's mod P. So now Q and P have to have some sort of relationship, but this doesn't matter for now. I just want to look at the look at how these functions look. Now in lattices, there's also a function, and it also maps elements in this ring, so k elements in this ring, but instead of them being in the exponent, they get multiplied by some random a's, right? So you just sum of ai si. So that's the lattice one-way function. So in discrete log, we say this f is one way. So it's hard to get the discrete log. For lattices, f is one way if the SI have small coefficients. That's the big difference. That it's if the SI do not have to have small coefficients, this is a trivial function to invert. But if they have small coefficients, then the function is one way. And sort of as an additional algebraic bonus, this ring R prime, this that is the output of the sum of AISIs, is exactly the ring R except mod P. So it's you can think of it as a subring of R, or a coset more properly. So and this nice algebraic structure is what gives lattices a lot of sort of flexibility, and gives them a lot of that's why you can construct many schemes you cannot construct from discrete log, basically based on lattices. So discrete log does not have this nice algebraic bonus, because the ring you map into is pretty different than the original. And then another difference is that so these Q and P in discrete log have to be exponentially large, so 2 to the 256. But for lattices, we want them to be small, like somewhere between 2 to the 12 and 2 to the 32. Of course, you can take them to be large, but you don't need to. Okay, so this is so if you just look at the ring LWE relation, this is what we're going to try to prove in zero knowledge. We're going to try to prove knowledge that I know the SIs, so that the sum of AISIs is whatever is the output. Okay, so somewhat more generally, you can generalize lattices. So here it was just sum of AISIs, but I can actually have a matrix, right? I can have just a matrix of AIs, and this is generally what's done. This is the module LWE, module cis assumption, what is used in practice a lot. Okay, but that's not important. I mean, you can just ignore this, pretend this matrix A is just one row. It's fine for now. All right, so now let's just go through the discrete log protocol quickly. This is the Schnorr Protocol for proving G to the S equals H. And I'm just going to use one S, right? So not a vector of them, just one. But if it's a vector, it's really the same, very similar protocol. You just have to have more masking vectors. Okay, so the prover knows G and S, the verifier knows G and H. So, I mean, I guess you know this, right? So the prover picks a random Y and then computes G to the Y and sends the output, right? So Y is the mask, is going to mask the S. The verifier chooses a random challenge. And then the prover computes SC plus Y, okay, in ZQ. And then because Q and P have a particular algebraic property, algebraic connection, the verifier can check that G to the Z is H to the C times W mod P. Okay. So, and the correctness works out if you just look at the exponents. G to the SC plus Y equals G to the SC times G to the Y, with all the moduli kind of working out. All right. So that's discrete log. And it's zero knowledge because intuitively the mask Y hides S because it's uniform in ZQ, right? So, and then you can formally prove it by generating a random C and Z, and then setting W to be the whatever it needs to be, G to the Z over H of C, so that verification works. And then you can prove that the triplet WCZ really has the same distribution as in the protocol. And it's really crucial that Y plus SC is uniform in ZQ. Oh, yeah, so it should be ZQ, sorry, generating CZ and ZQ. Okay, so the Schnorr protocol, the extraction, how do you prove that, if the prover succeeds, that he really does know does no S. Well, and this is the usual rewinding trick. He answers for one challenge, and then you rewind him and you ask him another challenge, C prime. And then he outputs Z prime. And now basically in the extraction you have two equations for the same W. And so you can basically combine the two equations, you get rid of the W, and you get that G to the Z minus Z prime divided by C minus C prime is H. And this quotient, that's S. Okay, so this is the standard Schnorr Protocol from more than 20 years ago. And it's kind of the basic discrete log zero knowledge proof, the fundamental foundational thing. So if we want to do the same thing for lattices, let's try to do it, right? So let's try the same zero knowledge proof over this other ring. So the prover has A and S, and the verifier has A and T, such that AS equals T. Okay, so AS equals T is what we're going to try to prove. So we do the same thing. So the prover is going to try to get some mask Y. The intuition is this Y is going to mask the S. And then he's going to compute A times Y. And send the W over. Now the verifier is going to create a challenge from the ring. So I'm not saying how you sample yet, because as you can see, this ring is not a finite ring, right? But there's some sampling happening. And then the prover is going to send SC plus Y, just like before, this Z. And the verifier can check that AZ equals TC plus W, because all the math works out exactly as before. Okay, good. So correctness, all good. So because A times SC plus Y is equal to ASC plus AY. Okay, so there's no problem there. So what about zero knowledge, right? So the first thing to note is that Z, this output Z, must have small coefficients. Otherwise, forging is trivial. Remember, this ring LWE, ring cis problem is only hard if the secrets are small, have small coefficients. And you can also see why it's not hard. The converse is it's not hard if it has large coefficients. So because if it has large coefficients, then it's very easy to find, just using Gaussian elimination, the solution to AZ equals TC plus W. You compute TC plus W and you solve for Z mod P, right? The hard part is that Z has to be small. Okay, so this implies that that Z has to have small coefficients. Well, since Z equals SC plus Y, this implies that Y should also have small coefficients with respect to. So when I say small, I mean with respect to P. Okay. So, but now if they have small coefficients, SC plus Y is not going to be uniform, because SC, if the coefficients of Y are small, then SC is kind of going to stick out. So before, in discrete log case, it all came from a uniform ring. So Y was uniform in the ring, SC was something, and Y plus SC was, of course, uniform. But now Y is something with small coefficients, and SC will stick out. So this could leak information about S. So of course, you could make Y exponentially larger than SC, so SC only sticks out a little bit, but this is very bad for efficiency. So we don't want to do that. So there's a better solution, and it's kind of to use rejection sampling to make the distribution of Z independent of S. So let me just explain intuitively what rejection sampling is. So now let's suppose that I want to sample forget lattices, forget everything else. This is just, I'm just going to explain what rejection sampling is for those who don't know. So let's say you want to sample a uniformly list triangle. But I don't have a sampler that can sample uniformly the triangle. I only have a sampler that can sample uniformly in a square. But I don't want a square, I want a triangle. So what do? Well, I can use rejection sampling. So the idea is I'm going to place my triangle inside the square. then do the sampling in the square, and throw out all the dots that are outside the triangle. And the idea is that all the dots inside the triangle are uniformly red. Okay. Now, of course, I'm throwing out, if a dot lands outside the triangle, I have to throw it out. This means that maybe the sampling is going to take much longer than it needs to, right? Because I only, to sample one point, I have to wait until I get a point in the square that's also in the triangle. So if the area of this triangle is much smaller, this is not good. Okay, so this is basic rejection sampling. But it has, like, sort of, there's an important consequence that we need, that sort of this implies in our zero knowledge proof, is the following. That suppose, so you have this triangle in a square, right? But so it's in the square, but maybe there's also a shifted square from which you could be sampling, right? So let's say there's this blue square and a red square they're shifted, but the triangle is inside both of them. So the point is that any shifted square distribution results in the same triangle distribution, right? So if you look at this triangle, the distribution is uniform regardless of which red or blue square you were using in the beginning. And actually the distribution is the same, right? So you cannot really, someone who's looking at the distribution in the triangle cannot tell if the original one was the square, the red square, or the blue square. Okay, so this is important. And here's how this analogy is going to be used in the zero knowledge proof. So notice that SC plus Y, so Y is chosen sort of from some ring, from some distribution, and then it gets shifted by SC. And so now so this distribution of Z is now either this red square or the blue square, depending on what S is and SC is, right? But if you do rejection sampling inside some triangle, quote unquote, I mean, there's no triangle here, but from the previous slide, then it will not be known. Someone who looks at the final distribution will not know which square you were sampling from. So basically, we will not know what the S was. So basically, the distribution is going to be independent of S, right? So that's what we do. So we create a Z, which is SC plus Y, and then rejection sampling and restart if necessary. So you want a rejection sample into some some shape that's inside all the possible shifts. Okay, so so Y plus SC is a shifted distribution. Use rejection sampling to get a non-shifted one. So that's the basic idea, but of course there's more interesting things you can do. You can not just do this all or nothing rejection sampling where you either output if something in the triangle or not, or don't output if it's not, but you can do get some better distributions that allow you to output smaller Z's. If you do something else, if the original distribution is a Gaussian or maybe bimodal Gaussian or rounded Gaussian, so these are all tricks to get smaller Z's, which is what you want. Okay, so now we're going to do the same proof. So now we know how to get zero knowledge. That's rejection sampling. Now let's see what the second problem is, and it's in the extraction. What are we actually proving? Okay, so what we're actually proving, let's do the rewinding trick, the extraction trick. So in the first step, the prover we get some transcript with some challenge, C. So we get a Z back from the prover so that AZ equals TC plus W, and Z is small. And then in the second, after the rewinding, in the second transcript, we get a Z prime so that AZ prime equals TC prime plus W, and Z prime is small. So now we can combine the two to get A times Z minus Z prime equals T times C minus C prime. And then just like for the discrete log case, we divide by C minus C prime, and we get, some pre-image of T. But the problem is that C minus C prime may not be invertible. That's the first problem, but okay, let's say a small problem. But the bigger problem is that S is not small, because just because C and C prime are small, the division by them is not. Right? So this was never a problem in the discrete log world because we didn't care whether the discrete log was small or not. We just needed some discrete log. But for lattices, we really care that S is small. So this is not a proof that I know a small s so that AS equals T. This is a proof of something else, right? But it's still meaningful, right? because you still get something that's hard. It's not exactly the statement that the prover claims he knows, but it's a related statement that's still difficult. So you kind of proving that I know something small with z minus z prime that's equal to a times it is t times something small, right? So it's not exactly t, but it's t times something. So it's not really what you want, but it's still meaningful. And actually, this is the basis of, once you have this, you can then do some other things. And this is what I'll sort of show on the next slide. I won't show how to do it, but I'll sort of show what the sequence of, transformations is to get something we want. So here's what we have now, right? So we have this approximate proof. This is what I showed. We're given AS equals T, but I don't prove knowledge of an S. I prove knowledge of a small s and C, so that AS prime equals TC. But this is already good enough for digital signatures. And so this was the first application of this idea in lattices. And so from that, you really get, so eventually, a series of few improvements, you really get like 3 kilobyte digital signatures just from this, sort of directly from this. This gives you a 128-bit secure 3 kilobyte digital signature scheme. Okay, but this is not what you want to prove. All right, so let's see what else you can do with it. And something else you can do is a commitment scheme. So you can create a commitment scheme to vectors over R. Right, and you can do linear proofs with them, and they're also fairly efficient. So commitment schemes, they don't really care about what exactly you're proving. Here we don't care exactly what you're proving. You just want a commitment scheme, and you can do it. Okay, so now once you have this commitment scheme, so this was shown, maybe last year. It's kind of progress went very fast. That now, once you have these, you can use these commitment schemes as a sub protocol in getting exactly what you want. So you want to prove knowledge of S so that AS equals T. You can do it, using commitment scheme and then, a lot of other techniques, a few other techniques. But if you notice, what happens is if you would just want to prove this knowledge of S, the proof size grows by a lot. So now it's about 300 kilobytes, right? So the digital signatures, the proof, signature size, think of it as a proof, was about 3 kilobytes. Now it's 100 times larger, right? So okay, but it was good. It was a good start. So something that was done last year and this year is actually from these commitment schemes, you can do multiplicative proofs. So you can prove, if you have a commitment to S1 and S2 and S3, you can prove that S1 times S2 is S3. So that was also good. And the commitment proofs, these multiplicative proofs maybe were about 50 kilobytes. And then using multiplicative proofs and other results, you could get something called unstructured proofs. You can prove various relationships over your commitments, over your committed values. And then, so using all of those ideas together, you can again get these exact proofs which are now about 50 kilobytes. So it's still bit larger than the 3 kilobyte for digital signatures, but it's definitely going, it has, in just 1 year has decreased, by a factor of 6. Maybe now we can do even a little better. Okay, so basically, so starting with these approximate proofs, we go to commitments, and then once you have commitments, you can use other techniques to prove various relationships on these committed values, and that allows you to do exact proofs eventually. And now some other things you can do. So, okay, so this gives you exact proofs, but why do you care about proving exact, why do you want to do exact proofs for lattices? It's somewhat, maybe you don't care. You care about proving actual relations. So something, some recent work we've done is we can now prove integer relations. So nothing to do with lattices, right? So let's say you have, commitments, these hash and prove relation, commit and prove relations, sorry. You have three integers, arbitrary size, let's say, and you commit to them, and you prove that the first two, the product of the first two is the third, or the sum of the first two is the third, right? So this is something we can do with, all starting from these approximate proofs. And actually, this is I think a scenario where these lattice-based proofs are probably the best quantum safe proofs right now for these particular problems. So for example, so we have an implementation So let's say I just want to commit to three 32-bit integers, A, B, C, and I want to prove that A plus B equals C, right? So this comes up very often in, let's see, the multi-party computation, or even just if you want to, actually do some proofs on the, about just some statements. I have some money in my bank account and I'm bidding on some item in an auction, and I want to prove that that I have enough money, something like that. Or somewhat more complicated relations if you have, since you already have addition and multiplication. So, and the nice thing is that the proof time is less than 3 milliseconds to prove these relations. And the proof size is also quite small. So about 11 kilobytes or 15 kilobytes for multiplication. So something to recall is that Ligero and Aurora, these were the PCP-based schemes, actually require just a few hundred milliseconds just to prove a commitment, just to prove knowledge of a commitment. So this is clearly already better, right? So it's clearly orders of magnitude better than the generic PCP-based zero knowledge proofs. But we have a disadvantage because our commitment sizes grow linearly. So if you want to prove 50 instances, our proof size is going to grow sort of as going to be about 50 times larger. Whereas Ligero and Aurora are sublinear, so their commitment sizes grow sublinearly. So maybe for 50 of these equations, they will be much shorter. In terms of time, I think lattice schemes will be much faster, and so they could be useful already useful in cases where time is more important than proof size. But I'm hoping that eventually we can also get some nice sublinear practical results from lattices. Okay, so that was some example, and so I also want to say, give an example of another kind of line of research, which is definitely much, not as hopeful about, but maybe somebody will see something that we have not. Right, so this is a middle ground between classical and quantum safe. Okay, so here's this diagram about where we are now. We're just trying to make quantum computers good for something, and we certainly have not reached the point where quantum computers can break crypto. And the main reason is that I said we want to do something now about this is that this store now, decrypt later attack. So what if we just want to prevent that? What if we don't want to design schemes that are useful after quantum computers are built, but really that are useful right now and don't succumb to this store now, decrypt later attack? So the idea is the following: you want to use a one-way function which is quantum safe, but maybe the zero knowledge proof is not quite a quantum safe proof. So here's what I mean. So you have a quantum safe one-way function, let's say a commitment scheme, and then you give a zero knowledge proof of knowledge that you know X, and the proof is complete. Okay, of course, but it's sound based on a classical assumption. So classical soundness. If somebody had a quantum computer, they could forge, but no one does yet, so they cannot forge. Okay, and the important thing is, for preventing this store now, decrypt later attacks, is that it's statistically hidden, right? So so the zero knowledge proof is information theoretically zero knowledge, or at least quantum safe zero. So if we had these three properties, then we would have complete sound and zero knowledge right now, right? Because nobody can break classical assumptions. We would have completeness, soundness, and zero knowledge, before Shor's algorithm breaks crypto. Once crypto is broken, classical crypto is broken, we won't have soundness anymore. We'll still have zero knowledge and completeness. And this kind of means, and the important thing is that all the proofs that were done before do not leak anything in the future either, because they are statistically hidden. And so another point that, maybe this proof, even if it is just classically sound, maybe can still be useful, because even if we can break discrete log in the future, it doesn't mean that we can break it fast, right? So, so some estimates say that, we can break discrete log, maybe it'll take a couple of hours to break it. But so if you kind of require the proof to be done fast, it could still be sound. This is definitely an iffy assumption, because so you don't want to protect very important things with it, but it still has some use, right? But the important thing is that it really prevents the store now, decrypt later attack. So you really could be using these proofs now without worrying that the information is somehow going to be leaked in the future. So, and we had this idea for how to do this before. So let's say you want to prove this typical lattice equation, this AS equals T. So the first thing we do is instead of working in this polynomial, ring mod x to the n plus 1 and q, we change this equation to work just over the polynomial ring. Then you can do a Peterson commitment of the coefficients to the secret coefficients using elliptic curve crypto, right? So just do a Peterson commitment, right? Discrete log-based commitment. Once you have that, the verifier sends some random challenge from a big field, and then we use this bulletproof's zero knowledge proof, or I guess you could use any other zero knowledge proof, to prove the polynomial equality of the values in C over Zx. So you want to prove equality basically over Zx of this polynomial relation, right? Because we have this polynomial relation that's in the ring C of x, evaluated at A, right? So the advantage of this is that now we're just doing a pure discrete log proof, right? We converted the lattice proof to discrete log 1, and we're doing a pure discrete log proof. And if you can do it, it implies the original state. And the nice thing is that it's very short. So, it uses less than 2 kilobytes for the proof. But the bad thing is it's very, very slow. So even just proving this basic relation takes, maybe even up to a minute to prove basic lattice relations. And if you want to do something much more interesting, it would take a significant amount longer. So I think if this idea is to work, you have to use some other technique for the classical part, or maybe have a better idea for how to convert the lattice equation to a discrete log 1. So we're kind of stuck here, and we don't know how to make it faster. But I'm kind of hopeful that maybe someone else does, someone who's much more of an expert in this classical zero knowledge proofs than I am. Right. So, but if you could do this, this would be good, especially if you believe that quantum computers are coming not in 10 years, but maybe in 40 years. So there's no reason to kind of move to the somewhat less efficient, purely lattice-based or purely, purely PCP-based constructions if quantum computers only come in 40 years. So maybe you just use something to prevent these harvesting store now, decrypt later attacks. So that's sort of a line of research that's possible. And that's kind of all I wanted to talk about today. So just some conclusions is that lattice-based zero knowledge research is just beginning. So this is really, I would say we're just at the foundation steps of for how to efficiently prove basic relations. So we kind of know how to prove, knowledge of a basic lattice relation. We can prove some addition multiplication of integers fairly well, but it's really that's really just the baby stuff, right? So some interesting thing that lattices can give us is speed, right? So an interesting question is, even if you don't care about quantum computing, can lattices be faster than discrete log or pairing based schemes? So I mean, they definitely are not going to be shorter, but could they be faster? Because they are faster for encryption than discrete log based schemes by a good factor. So then another question is about this middle ground approach that I just discussed. So especially if you don't believe, you're not a firm believer that quantum is coming very fast, maybe you want to consider that, but we have really not explored it very much. And, maybe some non-bulletproofs approach is something that could work. And another big area of research is succinct proofs. So SNARKs, so something like SNARKs, succinct non-interactive zero knowledge. There's some theoretical works with asymptotically short proofs, but they are not practical yet. So getting something nice and practical from lattices, or at least better than the PCP, than the hash function PCP approach, would be very, very interesting. And so I just really gave the high level sort of overview in this talk. And just listed some supplementary resources if you want to learn a little, get a little more in depth about lattice-based, about zero knowledge. there's a nice document by the Zero Knowledge standardization body. They just kind of put out some document. I'm not affiliated with them at all, but that lists here are the types of zero knowledge proofs we can do. Here are the problems we're trying to solve, etc. So maybe something interesting, worthwhile reading. So if you want to just learn about lattices, so I have a basic tutorial on my webpage, just about encryption and signatures. And if you want more details on zero knowledge, you can look at a link. There was a lattice school about practical lattice cryptography at Simons Institute at Berkeley, and it's all online. All the talks are online, so that may also be an interesting resource. Yeah, so that's it for me. So thank you again to the organizers for inviting me, and you have a good rest of the conference.
Thank you very much. Thank you, Vadim, for excellent talk. Yeah, I'm sure we will have audience like to ask you questions. For any of you, if you like to ask questions, please either raise your hand or type your question in chat or the Q&A box. Okay, probably, yes, Stephanie will keep eyes on the attendee list and see anybody want to ask questions. So before they prepare their question, probably Vadim, I take this opportunity to ask you first question. Yeah, I know your research is focused on to make lattice-based crypto practical. Yeah. So now we have a NIST standardization effort, which is probably going to leading to a few recommendations by NIST, and people were likely to follow their recommendations. But this research is still ongoing. I would like you to comment from your point of view, whether we still have a bigger room to improve the lattice-based chain and signatures. So if that is the case, after NIST's the standardization after finished, so people will use some scheme which may not be the best by that time. So what can we do?
Yeah, okay, so that's a good question. So I would say that in terms of sizes, parameter sizes, so outputs, keys and ciphertext and signatures, it would be surprising if you could do much better than what we have now. I mean, of course, there could be some completely different technique, and okay, then there's nothing you can do about that. But in terms of sizes, I mean, you can always, tweak a little bit, have a little fewer bytes, make a stronger assumption. But I think we're basically there. I would be very surprised if we can achieve something even like, I don't know, even like 30% reduction. That would be surprising. So I think that's sort of fixed. What could happen is in terms of speed. Speed could definitely increase. There could be some other, it did some somewhat different protocols, use different rings, and maybe, I don't know, just do things a little bit differently that can increase speed. And then people will say, I really do care. Maybe some will say, look, I really do care that something is the fastest, and I want to use that. I don't, I want something that's 3 times faster than the current NIST standard. And then I think there's going to be there will be definitely a good reason to have other standards. Maybe IEEE standard or whatever, to standardize these other variations of these NIST schemes. So that will happen. In terms of better sizes, that to me, that would be much less likely.
Okay, thank you. And I see somebody already typed their question in the chat box. Yeah, can you see the chat box?
This is
if
so
you can't, you probably
yeah.
share your screen, then you will be able to see.
So Stephen, he copied the question. Is it about in round 3? Are you planning to modify or add anything to dilithium?
Yes, that's a question.
Yeah. Okay, so there's that question. So we are modifying the parameters in dilithium. Yeah, I mean, how we chose the parameters, I mean, we will definitely have scripts to explain what the security of these parameters are. But in terms of how we chose them, a lot of things in lattice, how to choose parameters in lattices is really you have some ballpark idea of what they should be. You try them, and then you see if you can improve them, manually, right? So there's really there's no script for choosing parameters. There's scripts for testing how secure something is, but for choosing them, you just have to kind of have intuition to get something in before, and then just keep modifying it back and forth. I mean, this is kind of what we've been doing. I just check it. No, not secure. Oh no, it takes too much rejection sampling. So yeah, there's nothing other than guess and check that you can do.
David, I see you put some comments in the chat box because you are a panelist, so you can just talk. David Nakachi.
Nothing, it was just a virtual upload to Vadim for this super presentation.
Oh, thank you. Okay, so I'm going to stop sharing, and then you're saying I can see things? Okay.
Yeah, you can see chat box, you can
yes.
Q&A.
Okay, I see. So does lattice-based zero-knowledge proof have a unique nature? Is it different from previous schemes? So I'm not quite sure what that means, but you definitely cannot just port other schemes to zero knowledge. So as I hope I kind of showed, is that it has the same high-level structure as discrete log proofs, at least for the basic stuff, but some things go wrong, especially in terms of you have to keep the sizes small, and you have to keep the keep the sizes small, and this invertibility comes in, and you have to solve these problems. So basically, the hard part about lattice cryptography is to solve these problems that come up when you try to do Schnorr type proofs. And then can I comment on hybrid schemes in case some of this quantum safe turns out to be flawed? Yeah, so I guess by hybrid you mean use the quantum safe stuff together with the current lattice, elliptic curve or factoring based stuff. So I think that is definitely what's going to happen, or what should happen in the beginning, right? Until I'd say until maybe 5 to 10 years after the standard, maybe okay, we'll feel comfortable enough with these quantum safe schemes. But until then, you really should be using it in tandem with elliptic curve or RSA stuff, just to make sure you're not easier than than what you're doing now. So you definitely don't want to throw out the current stuff for at least 5 to 10 years. But after that, maybe there'll be enough research that we'll feel confident sort of taking off the training wheels and just using the quantum safe stuff. All right. Yeah.
Any more questions? Okay, if we don't have any immediate question now, since our time is also run out, and we need to close this session, but I would like to let you know you can still carry on discuss with Vadim. You can put your questions in Slack. We have a unique channel for this keynote. All right. Thank you very much, Vadim. Thank you very much for everybody attend the session and involved in discussions. This is great.
Thanks, Lee.
Thank you.